In the first module, we looked at energy that you've done in grade 10, and then we also looked at the new definition of work and how to use that definition in order to solve work problems. In the second module, we're going to look at methods and concepts that you've done in the topics of vectors and Newton in grade 11, and we will also discuss how to use those methods and concepts in order to calculate the net work or the total work done on an object. We will look at calculations to calculate the net work on a horizontal surface, and then also to calculate the net work on an incline. And then briefly we will have to just do a little bit of revision on free body diagrams that you've done in grade 11. We will consider two situations, and the first situation is where an applied force at an angle acts on an object and causes a displacement of delta x for the object. Now, if you look at the free body diagram of all the forces acting onto that object while it is displaced, you will see that there are actually four forces: the applied force at an angle, normal force, kinetic friction, and gravity. And in grade 11 you learned that if you have an applied force at an angle, you can replace that force with two components of the force, and that would be the horizontal component and the vertical component of the original force. The aim here is to calculate the total work or the net work done by all the forces or components of forces that are acting on an object while it is displaced. And you have to decide which of these forces to include in your calculations. But you already know that those forces that are acting perpendicular to the displacement of the object can be ignored because the cos of 90 degrees is equal to 0. So the only forces that you will include here are those forces that are acting in a horizontal direction onto this object. So in this case, we will include the horizontal component of the applied force as well as the kinetic friction, because those two forces are the forces that are acting onto this object in a horizontal direction while it is displaced. So when you have any example where a force is applied at an angle at an object that is displaced horizontally, and you have to calculate the total work or the net work done onto this object, you will start by calculating the horizontal component of the applied force and consider all the other horizontal forces in order to calculate the net force acting onto this object. And you will use that net force to calculate the net work done onto this object. Calculate the net work done on the object in the diagram to displace the object by 5 meters on a rough horizontal surface. On a rough horizontal surface, this means that there's friction involved, and you can see in the diagram that kinetic friction of 5 Newton is involved. You can also see in the diagram that you have a force applied of 50 Newton at an angle of 25 degrees to the horizontal. So if we have a force at an angle, we calculate the horizontal component of that force, which is 50 times by the cos of 25 degrees. So to calculate the net work, we need the net force, and in this case the net force is the horizontal component of the applied force, which is 50 cos 25, and then minus 5 Newton, which is the friction, the kinetic friction. Minus because it's in the opposite direction to the displacement. And we multiply that by the displacement, which is 5 meters, multiplied by the cos of 0 degrees. And that gives us a total or a net work done of 201.58 joule. A young man tries to move a heavy drum, and the drum has a mass of 80 kilograms. The young man applies a horizontal force of 60 Newton to the drum, and the drum experiences kinetic friction of 35 Newton. He displaces the drum a distance of 5 meters. Draw a free body diagram and present and label all the forces that act on the drum. When you have to draw a free body diagram or a free force diagram, you will remember from grade 11 that you use a small dot or a small square to represent the object, and then you have to use arrows pointing from this dot or square, and the direction of these arrows will represent the direction of the different forces. The labels are important. There are several acceptable labels. You have to choose your label that you're going to stick to. I prefer these ones, and those are the ones that I stick to. Alright, we have an applied force to the right, a normal force, kinetic friction to the left, and gravity. The lengths of these arrows are important, but you don't have to draw them according to scale. We know that the applied force is 60 Newton to the right, and we know that kinetic friction is 35 Newton to the left. So the arrow to the right must be at least a little bit longer compared to the arrow to the left. Normal force and gravity have the same magnitudes, and therefore we use the same lengths of arrows to represent these two forces. Calculate the work done by each of the forces. Now, if we have to calculate the work done by gravity first, we know that gravity acts perpendicular to the displacement of this object. So when we calculate the work done by gravity, we will use the cos of 90 degrees, and the cos of 90 degrees is 0. So therefore the work done by gravity will be 0 joule. The normal force is also perpendicular to the displacement of this object. So if we calculate the work done by the normal force, we will also use the cos of 90 degrees, and that will also give us that the work done by the normal force is 0 joule. The direction of the applied force is in the same direction as the displacement of this object, and therefore when we calculate the work done by the applied force, it will be 60 Newton, which is the applied force, multiplied by the displacement of 5 meters, multiplied by the cos of 0 degrees, because the direction of the applied force is the same as the direction of the displacement, and that gives us work done by the applied force of 300 joule. The direction of kinetic friction is always opposite to the direction of the displacement, and therefore when we calculate the work done by kinetic friction, it will be 35 Newton for the kinetic friction multiplied by a displacement of 5 multiplied by the cos of 180 degrees, because the angle between the displacement and the force is 180 degrees, and that gives us negative work of 175 joule. Calculate the net work done on the drum by all the forces. We will include only the horizontal forces because we know that this object has a displacement in a horizontal direction. So to calculate the net force, we use the 60 Newton of the applied force, subtract the kinetic friction because it's in the opposite direction to the applied force, multiply that by the displacement of 5, multiply by the cos of 0 because the net force is in the same direction as the displacement, and that gives us net work done of 125 joule. You could, however, also use the work done by the applied force and the work done by the kinetic friction that you already calculated in order to determine what the net work was. So the work done by the applied force was 300 joule, and we know that negative work of 175 joule was done by the kinetic friction, and that will also give you a net work of 125 joule. The young man changes the angle at which the applied force is acting on the drum, but still applies the same force onto the 80 kilogram drum. The angle of the applied force is at 20 degrees with the horizontal and causes the friction between the drum and the floor to increase to 45 Newton. The man pushes the drum to displace it the same distance of 5 meters. Calculate the net work done on the drum now by all the forces. In the free body diagram, we can see that this force is applied now at an angle of 20 degrees to the horizontal. Kinetic friction also increased to 45 Newton opposite to the displacement. So if we have a force applied at an angle, we start to calculate the horizontal component of that applied force. And we use this horizontal component together with the friction to calculate the net force applied to the object. So to calculate the work done, the net work done, we use the net force, which is the horizontal component of the applied force, which is 60 times cos of 20, and subtract 45 Newton, which is the new kinetic friction. We multiply this net force by 5, which is the displacement, and multiply that by the cos of 0 degrees, because the angle between the net force and the displacement is 0 degrees. And that gives us positive work of 56.91 joule. The second situation is where you have an object that moves up or down an incline. Now the principles of up and down movements are the same, but the direction of the displacement will be different and the amount of forces acting on the object will be different. So in this case, we have an object that's displaced delta x up the incline due to an applied force, and then the normal force, kinetic friction, and gravity are also forces that are acting on this object while it is displaced. With an object that is displaced on a horizontal surface due to an applied force at an angle, we calculate the components of that applied force. Now with an object on an incline, we calculate the components of gravity, and we have a perpendicular component and a parallel component. So now we have to decide which of these forces or components of forces we have to include in our calculation to determine the total or the net work. Now we already know that all the forces that are acting perpendicular to the displacement of the object can be ignored because the cos of 90 degrees is equal to 0. So we only include those forces or components of forces that are acting in the same direction or opposite to the direction of the displacement of the object. So in this case, we have an applied force, we have kinetic friction, and the parallel component of gravity. A lady pushes her grocery trolley in the parking lot of a shopping center to a vehicle. The parking lot has a driveway built at an incline of 25 degrees. The mass of the trolley with the groceries is 125 kilogram. The kinetic friction acting on the trolley is 40 Newton. She pushes the trolley at a constant velocity for a distance of 0.04 kilometers up the driveway. Draw a free force diagram of all the forces acting on the trolley while the trolley is pushed up the driveway. If the question was to draw a force diagram, you would draw a trolley and arrows to indicate where and how the forces are acting on this trolley. The question, however, was to draw a free force diagram, and you will remember that a free force diagram or a free body diagram is where you use a small dot or square to represent the object and arrows pointing from this dot or square to illustrate all the forces and the directions of the forces that are acting on the object. So in this case, we have 4 forces. The directions of these arrows are important, as well as the labels that you use. In this case, we have an applied force, we have a normal force which is perpendicular to the incline, we have kinetic friction, and gravity. Calculate the net work done on the trolley while the forces are applied to the trolley. So if we look at the free force diagram, there are 2 forces that can do work on the trolley. It's the applied force and kinetic friction. We can also calculate the two components of gravity. So the parallel component of gravity is also another force that can do work on the trolley. To calculate the net work done by the forces on the trolley, we have to calculate the net force, but nowhere did they give us the force that was applied by the lady onto the grocery trolley. So we have to read, and you have to see that this trolley is moving at a constant velocity. Because with a constant velocity, we know that the net force acting on the trolley must be equal to 0, and therefore we substitute a net force of 0 multiplied by a displacement of 40 multiplied by the cos of 0. And therefore the net work done on this trolley will be 0 joule. Calculate the work done on the trolley by the lady. Now, in order to calculate the work done by the lady, we need to know what the force was that she applied to the trolley. If we look at the diagram, we can see that the net force will be the applied force plus the kinetic friction and the parallel component of gravity. We can calculate the parallel component of gravity. It's the weight of 125 times 9.8 times by the sin of 25 degrees to give us the parallel component of gravity. And we do know what friction was. That was 40 Newton. And both of these forces were against the motion of the object. So therefore we substitute negative signs for these two forces, and we calculate the force applied by the lady as 557,707 Newton. Now you will see that I don't round the answer yet, because this was not the answer to the question. The question was to calculate the work done by the lady. So the work done by the lady is this force of 557,707 multiplied by a displacement of 40 meters multiplied by the cos of 0, because the displacement and the applied force are in the same direction. That gives us work done by the applied force of 22,308,29 joule. And now I can round the answer to 2 digits. A grade 12 learner walks up a staircase at school. He maintains a constant velocity. The first floor is 3.5 meters from the ground floor, and the school bag has a mass of 8 kilograms. Calculate the work done by the learner on the school bag to carry the bag to the first floor. The object here is a school bag, and there are two forces acting on the school bag. It's the applied force and then gravity. But we are only interested in the applied force because we have to calculate the work done by the learner on the school bag. And they didn't give us the applied force. They only said that he maintains a constant velocity. So for a constant velocity, we already know that the net force acting on the school bag must be equal to 0. We can calculate the weight of the school bag because it's 8 kilograms times by 9.8. And we know that the weight or gravity is downwards, therefore the force applied by the learner must be equal to 78.4 Newton. So the work done by the learner on the school bag will be the applied force by the learner on the school bag multiplied by the displacement multiplied by the cos of the angle. Now the applied force is 78.4 Newton, and then the displacement of the school bag in the direction of the applied force. Remember, the applied force is upwards, so the displacement of this school bag upwards is 3.5 meters. And then we can say multiply by cos of 0 degrees because the displacement and the applied force are both in the same direction. And that gives us 274.4 joule. You can, however, use the 6 meters up the flight of stairs as the displacement of the school bag. So to challenge your mathematics a little bit, you can use this displacement of 6 meters and the applied force, which is upwards. But then you have to go and calculate the angle between the applied force and the displacement. So you will have to use these two distances that you've got and the triangle in order to get the different angles of this triangle, and that will help you to get the angle between the applied force and the displacement, and that will also give you the exact same work done by the applied force of 274.4 joule. Calculate the work done by gravity on the school bag while the learner carries the bag to the first floor. Right, to calculate the work done by gravity, we do know what the force of gravity is, the weight of the object. It's 8 times 9.8, and then the work done by gravity is just that force, the weight, multiplied by the displacement of 3.5, and then the angle between the force downwards and the displacement upwards is 180 degrees. And that gives us negative work done by gravity of 274.4 joule while the school bag is moving up. Final question. Calculate the net work done on the school bag to carry the bag to the first floor. So there are two forces acting on the school bag, and we know that it's moving at a constant velocity. So for the constant velocity, we know that the net force acting on the school bag must be equal to 0. And therefore, the net work done will be equal to 0 times 3.5 times the cos of 0, and that gives us 0 joule. You can, however, also calculate the net work by adding the work done by the applied force to the work done by gravity. And we know the applied force will do 274.4 joules of work, and gravity, while the school bag is moving upwards to the first floor, will do negative work of 274.4 joule, and that also gives you a value of 0 joule. If you are an educator that would like to inquire about the use of these PowerPoint slideshows in your classroom, you may contact me at lawsandwonders@gmail.com. Please indicate if this topic was useful to you or not, and subscribe to my YouTube channel in order to stay informed about the release of my most recent videos.